This is the lecture video for Chapter 12, Liquids, Solids, and Intermolecular Forces. Here we'll be looking at the 4 different kinds of intermolecular forces and how they determine solubility and other physical properties. Then we'll take a look at calculating enthalpy values as a substance changes from one phase to another. If you're a clumsy person that knocks things over, then make sure that electronics and liquids are not around you at the same time. Another solution could be for you to become an astronaut and work in outer space. Here we could see that an astronaut is working in the International Space Station. He's floating around in the space station along with some water that he quote-unquote spilled. Now, why is it that this spilled water stays in a spherical shape? Why can't it float around and spread out at the same time? So these water molecules are attracted to each other. That's why the blob in the International Space Station stays intact as a spherical object if it's left undisturbed. So here in this chapter, we're going to take a look at the 4 different intermolecular forces, their varying strengths, and how they are dependent on a substance being either solid, liquid, or gas. We'll also take a look at how thermal energy, heat, and even kinetic energy play a part in determining the different phases of a substance. We'll be using H2O many times throughout this chapter. Here you can see in table 12.1, we have different physical characteristics of the 3 different phases of H2O. One thing to note would be the density. So generally speaking, with any substance, the density value would increase as the phase becomes more condensed. But here you could see with the solid H2O, it's less dense compared to the liquid H2O. And that's because of how the H2O molecules are arranged in ice. And we're going to be looking at that later in this chapter. Here are the different characteristics of gases, liquids, and solids. You should know from experience that in terms of gases and liquids, they take up the shape of their container. They are free-flowing. But for gases, the volume is indefinite, and we'll take a look at that in the next slide. Really, in this chapter, like I said before, we're going to take a look at the intermolecular forces that hold these molecules together and thus form the different states of matter. Taking a look at gases first, these molecules are very energetic. They bounce around in the container that they're in, and there's a lot of empty space. So this is what I meant before when I said that the shape is indefinite. We have some gas molecules here in a piston, and as the piston gets pressed down, the volume of the gas decreases because there's so much empty space. Liquid molecules can flow freely as well, but they are more compact. And they are so compact that liquids are considered incompressible. So here we have the same piston system. As it gets pressed down, the volume of the liquid does not change. There's not enough empty space for the volume of that liquid to change. So the takeaway here is that both liquids and gases take up the shape of their containers, but the volume of the liquid is fixed because it does not have as much empty space compared to a substance in the gaseous phase. Solids, on the other hand, are fixed in volume and in shape. Those molecules cannot move around, but they do have some kinetic energy that would allow them to vibrate in place. So because their shape and their volume are fixed, solids are incompressible. Here's a little introduction on the different types of solids. We have crystalline and amorphous. Crystalline you've seen before when we were taking a look at ionic compounds and salts, specifically the crystal lattice. So when you see crystalline solid, you know that there is a geometric pattern that can be seen throughout that solid. With amorphous, if we break down the word, A meaning not and morph meaning shape, here we don't see a regular pattern throughout the substance. Okay, and examples of these types of solids would be plastic and glass. So let's check for understanding. Which state of matter is compressible? So pause the video, take a moment to figure this out, and when you're ready for the answer, click play. Okay, so the answer is C, gas. And that's because there is a lot of empty space between the gaseous molecules compared to solid and liquid. There are two ways in changing the phase of a substance. The first way is to change the amount of kinetic energy in those particles. So this goes back to the chapter with enthalpy, kinetic energy, thermal energy. So let's take a look at a solid material. Those molecules will not move. There would be some vibration going on because those solid molecules do have kinetic energy. But what happens when we heat up that solid? Well, now those molecules will gain more kinetic energy. And if they have enough kinetic energy, then they could break off the solid. So we would see that as a solid melting to a liquid. Those molecules will have more freedom to move around. The same thing can be said with liquids. Liquid molecules will have intermolecular forces that hold them together. Well, what happens when you heat up a liquid? Those intermolecular forces will break at some point, and we see that as a liquid boiling into a gas. Now, the second way to change a phase is by changing the pressure. So here we're specifically looking at gases. If we increase the pressure, then we're also decreasing the volume of that gas. So think about the slide with the gas and the piston. Okay, when you increase the pressure, the volume of the gas decreases. And so then what happens to the gas molecules inside that piston? Well, now they're more likely to be hitting each other. Okay, and if they hit each other, they're more likely to stick together. They have a better chance of forming intermolecular forces with each other. So when you decrease the volume of the gas molecules can condense to a liquid. If understanding phase changes and how enthalpy is involved is too confusing to you, then draw a very basic picture like this to help you understand. So pretend that the substance that we have in these three beakers is H2O. Okay, so we have ice, water, and water vapor. How can we get from ice cubes to liquid water? Well, we're going to have to heat that up, right? and then boiling the water so that we get water vapor, we're also adding heat to that system. So going from left to right here in our arrangement, we have endothermic reactions. Now, what happens if we have liquid water, liquid H2O, and we want to create ice cubes? Well, you're gonna put that water in a freezer, right? So we're cooling it down. We're removing the heat from this system. So going from right to left, we have exothermic processes going on. For those of you that like to barbecue in your backyard, you probably have a liquid propane tank attached to your grill. Now, inside this tank is liquid propane set at 10 atm. That's a lot of pressure, and it's enough to keep the propane in liquid form. Now, what happens if you're at sea level and you open up this tank? Well, the outside pressure at sea level is 1 atm, so it's obviously lower than what's inside the tank. So when you open up that valve, some of the liquid propane turns into gas. There's enough freedom for the propane molecules to move around, and they would have enough kinetic energy to leave the tank as gaseous molecules. Let's check for understanding. Think of this question as something that's cumulative. It not only tests what you've learned in the previous slides, but also in previous chapters. So here we have a picture of liquid water. Which one of these pictures shows water vapor being emitted from a pot of boiling water? So pause the video, look at these 3 pictures very carefully, make your choice, and when you're ready for the answer, click play. The answer here is letter A. You can see that we still have 1 red ball connected to 2 white balls, and that depicts 1 oxygen connected to 2 hydrogens, so we're still working with H2O. But this time it's in the gaseous phase because there's a lot more space in between these molecules compared to that of water. Okay, let's take a look at choice B. Here we have O2 gas and H2 gas. This is no good because this depicts a chemical change. Okay, if you have to change the formula, if you have to write a different formula compared to H2O, then we have a chemical change. Remember that boiling water is a physical change. You're only going from one phase to another. So the same thing can be said with letter C. Here we have individual atoms now, just oxygen atoms and hydrogen atoms. This does not depict the water vapor coming from a boiling pot of water. Now let's start taking a look at the different types of intermolecular forces. These are the forces found in between molecules, and they're the ones that determine the physical state of a substance. So if these intermolecular forces are strong in a substance, then most likely we're looking at something that's solid compared to gas. Another thing that we have to take a look at is the electrostatic forces that are involved in these molecules. So in other words, we have to figure out if our molecular structure has polarity. We also have to take a look at thermal energy. So intermolecular forces hold molecules together. And if they're strong enough, then they're most likely not going to move. However, if there's enough thermal energy, then these intermolecular forces can be overcome. They can break up. So we have to take a look at both of these things together, intermolecular forces and thermal energy, to see what type of phase we have when we're looking at a particular substance. So if these intermolecular forces are strong, if they're strong attractive forces, then we're going to need a lot of thermal energy to boil a liquid to its gaseous state, or melt a solid to its liquid state. So there are a lot of things that we have to consider as we change from one phase to another. So just think of opposites attracting each other when we're taking a look at intermolecular attractions and their strengths. If we start off with ions, the cation is going to be attracted to the anion. We already know that. Now, let's go into molecules, so not ions, molecules that are polar. The positive end of one molecule is going to be attracted to the negative end of a different molecule. And then even going further, if we take a look at nonpolar molecules, at some point they can have charges, but they're only temporary. So there are three types of interactions that we're going to be looking at here. Okay, but with all those interactions, we have to keep these relationships in mind. Okay, if we're dealing with a larger magnitude of charge, then we're going to have stronger attractions between these molecules. If the charges are far away from each other, then we're going to have weaker attractions. So from these relationships, you should remember an equation that we looked at several chapters ago. Okay, and that's Coulomb's law. So just think about it again. If the magnitudes of these charges are large, then we're going to need a lot of energy to break up those charges. If the distance between those charges are big, if it's long, then we don't need a lot of energy to break up the attraction. So a lot of students get confused between intermolecular forces and intramolecular forces. So when you see the prefix inter, you're going to think of two different molecules that are attracted to each other. So this dotted line represents some type of intermolecular force found between two different molecules. An intramolecular force would be something like a covalent bond. It's found within a molecule. And the force found here is a lot stronger compared to the force found between two molecules. So picture boiling water. The force that's being broken as the liquid is turning into gas would be the intermolecular forces, not the intramolecular forces. The heat that you're putting in is not strong enough to break this type of bond. Here are the four different intermolecular forces that we'll be looking at. As we go down the list, the attraction gets stronger. Also, as we go down the list, the molecules that we're looking at become more ionic. So the first type of force, dispersion forces, we're only looking at nonpolar molecules here. And as we go down the list, we start to see more polar molecules and then eventually ions. So our weakest type of intermolecular force is the dispersion force, which is also called a London force. And these types of forces can be seen in all molecules. So whether they're nonpolar, polar, or ionic, they all exhibit dispersion forces. Okay, but for us to understand this force better, we're mainly going to look at nonpolar molecules. So just to refresh, a nonpolar molecule does not have a negative end or a positive end. The electron density is spread evenly throughout that molecule. However, there are certain times where the electron density can be moved over to one side of that molecule. And when that happens, that one side that has the excess electron density, that side will have a partial negative charge. Now what's going to happen to the other side of that molecule? Well, it'll have a partial positive charge. So now we would have a temporary dipole moment. Just for a certain instance, we have a negative end and a positive end. Now when this happens to one molecule and there's a neighboring molecule close by, well, now that neighboring molecule will have an induced dipole. One end will also become negative, forcing the other end to be positive. Here's an example of how electrons can move throughout that electron cloud. And at one point, the electrons can be on one side of the molecule. So you can see here with frames 1 and 2, the electrons are spread out. But at frame 3, if we split up this molecule here, we see that on the left-hand side, we have a negative dipole moment. And on the other side, we would have a positive dipole moment. Now, what happens if that molecule, or the atom in this case, comes across another atom? Well, here we go. This was our original atom that has a dipole moment, temporary dipole moment. The positive end would attract the electrons of a neighboring atom, causing the neighboring atom to also have a temporary dipole moment. And it'll just cascade throughout that substance. So now we have to take a look at different factors that determine the magnitude of these instantaneous dipole moments. The first factor that we're going to look at is polarizability. Now when you see that term, you're going to think of the size of the electron cloud. If that cloud is really big, then it's really easy for more of those electrons to move to one side of the molecule or the atom so that two poles can be created. So if you have a molecule or an atom that has a very large molar mass, then it's easier to create those two different poles and thus have stronger attractions. Second thing is the shape of the molecule. If the molecule is a very long chain, then there will be more surface-to-surface contact between those different types of molecules. So if those molecules are in contact with each other, then there's more points of attraction. Sticking with polarizability, let's take a look at the noble gases. You can see that as we go down the column, the size of the atoms would increase. Also, the molar mass increases. You can also see that the boiling point increases. This tells us that for xenon, the intermolecular forces between the xenon atoms are stronger compared to what's found between helium atoms. And that again is due to polarizability. So pretend that helium is like a baseball and xenon is like a balloon. With helium, there's no way for you to move or like morph the baseball because a baseball is very hard. The electrons of helium are going to be very close to the nucleus. So that electron cloud cannot be manipulated very easily. Now, if we compare that to the balloon of xenon, you can, manipulate that balloon very easily. You could create, balloon shapes or balloon animals if you wanted to. The same idea with this big electron cloud. If more electrons can move to one side of a xenon atom, then we'll have a negative end and a positive end. So it doesn't matter what you have, whether it's an atom or a molecule, polar or nonpolar. If the molar mass of that substance increases, then the number of electrons would increase. And because of that, the electron cloud would get bigger. So as the electron cloud gets bigger, think of a balloon as opposed to a baseball. It's going to be easier for electrons to move to one side of that molecule and create a negative end and a positive end. Here we have 5 different hydrocarbons going from pentane to nonane. And you can see that the molar mass increases as we add more carbons and hydrogens to the molecule. And you could also see that the boiling points would increase as the molar mass increases. So it's not just molar mass that you have to look at, it's also the number of electrons, because the electron density would increase as molar mass increases. And remember, as we increase that electron cloud volume, then the easier it is, or the more polarizable the cloud would be in making a negative end and a positive end. So the hydrocarbons that we saw in the last slide were all straight-chained molecules. That's why they were labeled N-pentane or N-nonane. That N represents normal. So all of those carbons are in one straight chain. However, those hydrocarbons can also be branched. So pentane doesn't have to be straight carbons throughout the chain. There could be branches of carbon from one central atom. So we're going to take a look at that in just a bit, but you have to realize that branched chains would have lower boiling points than straight chains. Here we have 2 isomers for pentane. We have the straight chain and another one that is highly branched, neopentane. They both have the same molar mass, so same chemical formula, but take a look at their boiling points. The boiling point for the straight chain is higher than that of the branched. Now, why is that? Take a look at 2 molecules of the straight and pentane. Here you could see that there are infinite number of contact points. So there's a large area of interaction. There's a large area for attraction. Now compare that to 2 neopentane molecules. Here, think of this as 2 baseballs, or just 2 regular balls. You have smaller amount of interaction here. So there's less attraction for molecules that are branched compared to that of straight chain molecules. Let's do a bit of a review. Which halogen has the highest boiling point? Pause the video, reason this out, pick your answer, and when you're ready, click play. The answer is letter C, I2. This diatomic molecule has the largest molar mass out of the 3. So because it has a larger molar mass, it has more electrons, so it has more polarizability compared to Cl2 and Br2. And because of that, it would have stronger intermolecular forces compared to Cl2 and Br2. And how can we see that? By comparing the different boiling points of these three diatomic molecules. Here's our second type of intermolecular force, dipole-dipole. We'll see these in polar molecules. Okay, so polar molecules have a permanent dipole. So as a whole, dipole-dipole forces are going to be stronger than the London dispersion forces from before. Okay, now don't forget, polar molecules can exhibit those weaker dispersion forces. It's just that now polar molecules can also exhibit dipole-dipole forces. Okay, so with these polar molecules, we'll see that the boiling points and melting points are higher compared to nonpolar molecules. Again, nonpolar molecules only exhibit London dispersion forces. Here we have three different depictions of acetone. You can see that there are some nonpolar areas, but with this oxygen here, it makes the molecule polar. So this end right here, like how we see in the space-filling model, the end with the oxygen is going to be negative. The side with the hydrogens, that would be the positive portion. So now if you bring on another acetone molecule, the negative portion from one acetone molecule is attracted to the positive portion of a different acetone molecule. So here, this is where we have our dipole-dipole intermolecular force. Remember, when we're boiling or melting a substance, we're breaking the intermolecular forces. We're not breaking the intramolecular forces, which are covalent bonds. We're going to see that with polar molecules, they're going to exhibit London dispersion forces and dipole-dipole. So because they're going to have stronger intermolecular forces altogether, they're going to have higher boiling and melting points compared to nonpolar molecules, which only exhibit London dispersion forces. In comparing formaldehyde and ethane, we see that their molar masses are comparable, but take a look at their boiling points and melting points. For those of formaldehyde, they're higher because formaldehyde is a polar molecule. So both of these substances exhibit London dispersion forces, but formaldehyde also exhibits dipole-dipole. Here we're comparing 5 different molecules based on dipole moment and boiling point. You can see as we go from left to right, the dipole moment increases, and you could even see that in the electron distribution maps here. These red areas show where most of the electrons are located. So you could see for like dimethyl ether, the oxygen is right in the middle of the molecule, so you could see that the cloud is redder than the rest of the molecule. So for something like propane, this molecule is nonpolar, so its boiling point would be the lowest in the group. Acetonitrile here, the nitrogen, which is electronegative, more electronegative than the carbon and the hydrogens, it's found on one end of the molecule. So this dipole moment is the greatest out of the 5. And because of that, the boiling point, its boiling point is the highest out of the group. Even though the molar masses are relatively the same, acetonitrile would have the highest boiling point because it has the highest dipole moment. So it's important to incorporate electronegativity with molecular structure, because then you'd be able to figure out if you have a polar molecule or nonpolar molecule. And then from there, the different types of intermolecular forces involved in those molecules. And then from there, you would understand how soluble those molecules are with each other. So in a previous chapter, we saw that water cannot be dissolved with oil. Because water is a polar molecule, oil is nonpolar. So this is where like dissolves like comes in. If we want something to be dissolved in water, then it has to be polar. It has to have some kind of charge, just like water. So that's where we have hydrophilic groups, water-loving. In chapter 3, I believe, you were introduced to different families of organic compounds. So here are some of those families. Molecules that are nonpolar, we call those hydrophobic, so water-fearing groups. These are your hydrocarbons. Okay, so now let's go back to the different hydrophilic groups. Let's highlight several of these. So if you see OH in a chemical formula, most likely you're working with an alcohol. Okay, so here is the alcoholic group. We are in methanol here. So carbon is directly bonded to the oxygen, and the oxygen is directly bonded to a hydrogen. So here's our alcohol. Next, if you see CHO, then you're working with an aldehyde. So here we have acetaldehyde. Then we have a carbon that is doubly bonded to an oxygen, but that same carbon is singly bonded to a hydrogen. Okay, there is no hydrogen bonded with this oxygen here. It can be deceiving in the way that it's written out here in the formula, but when you draw out the structure, it looks like this. Next, we have a ketone. So what we have highlighted here is the polar portion of acetone. We have a carbon doubly bonded to an oxygen, but it's also singly bonded to other carbons. Next, we have COOH. That would be a carboxylic acid. So here we have formic acid or methanoic acid, that's the same thing. So it's like a combination of an alcohol with a ketone. Okay, so whatever is boxed out here, those are the polar portions of those molecules. We saw that molecules can have hydrophobic and hydrophilic portions. If there are more hydrophobic portions in that molecule, then most likely it won't be able to be dissolved in water. So you'd have to take a look at each molecule very carefully and decide if it can be dissolved in water or not. Here we have pentane. It is a hydrocarbon, so this is a nonpolar molecule. When we try to mix pentane with water in a beaker, at some point they are going to separate out. They will not mix because pentane again is nonpolar, water is polar. Here we have an electron distribution map for acetonitrile. You need to figure out how two of these molecules would interact with each other. So we know that this molecule is polar. Pause the video, take a look at the 4 situations very carefully, pick your answer, and when you're ready, press play. Okay, so we know that nitrogen is the most electronegative atom in this molecule here. So nitrogen is over here on the right-hand side. We could also tell because on this end, it's a little bit more red than the rest of the molecule. So this ball right here is nitrogen. Okay, so because, again, nitrogen is the most electronegative atom, this end is more negative. So that means this end is more positive. Okay, so our answer here is letter A. Like we said before, the nitrogen end is going to be negative. The hydrogen end would be positive. So if another acetonitrile molecule comes along, this negative end is going to be attracted to the positive end of another acetonitrile molecule. So this would be the orientation. Our answer here is letter A. Okay, so we have 3 molecules here. Which ones have dipole-dipole forces? We already know that all molecules have London dispersion forces, but not every molecule has dipole-dipole. So please pause the video, work everything out. When you're ready for the answers, click play. Okay, so for carbon dioxide, you need to draw out the Lewis structure, first of all. Then take a look to see if what we have is a polar molecule. So just by looking at the bonds, we know that the bonds are polar, but because we have a linear molecule, this molecule is non-polar. So there would be no dipole-dipole forces here. Okay, we would only have London dispersion forces. In drawing out CH2Cl2, we have a tetrahedral. We know that chlorine is more electronegative compared to the carbon and hydrogen. So the 2 chlorine ends would make the negative end. So that means the 2 hydrogens make the positive end. We have a polar molecule now. So because we have a polar molecule, we have dipole-dipole forces along with the dispersion forces. Here's our classic tetrahedral example, CH4, methane. The bonds are nearly nonpolar, but that doesn't even matter because since we have a tetrahedral molecule, all the bond angles are the same. So we have a nonpolar molecule. And because this is nonpolar, there are no dipole-dipole interactions here, just London dispersion forces. So let's do the same thing with these 3 molecules. Pause the video, figure out which ones have dipole-dipole forces, and when you're ready for the answer, click play. Okay, so for Ci4, this is a tetrahedral again. We have polar bonds because iodine is more electronegative, a lot more electronegative than carbon. But because we have a tetrahedral molecule, all the bond angles are the same, so this molecule is non-polar. It has polar bonds, but it is a non-polar molecule, so this does not have dipole-dipole forces. For CH3Cl, chlorine is the most electronegative atom in this molecule. So wherever the chlorine is, that's where the negative end would be. Where the hydrogens are, that's where the positive end would be. So we have a polar molecule here. So that means that CH3Cl has dipole-dipole forces. Now for HCl, this molecule is actually ionic, so the chlorine has the negative end, hydrogen has the positive end. So not only does this have London dispersion forces, it also has dipole-dipole. Our third type of intermolecular force is hydrogen bonding. So think of that as a special type of dipole-dipole interaction where we're specifically going to look at fluorine, oxygen, and nitrogen, all connected to a hydrogen. So this is very specific. Okay, a mnemonic that you can use to remember these three. These molecules like to have fun. So you're only going to see hydrogen bonding in molecules that have fluorine, oxygen, and nitrogen that are directly connected to hydrogen. Now, because these three elements are very electronegative, they're going to be the negative portion of the molecule. Here are two depictions of hydrogen bonding. This white ball here is hydrogen. This lime green ball can be either fluorine, oxygen, or nitrogen. Because these three are very electronegative, they will form the negative portion of the molecule while hydrogen is the positive. This dotted line right here, that represents the hydrogen bonding. Again, this is a type of intermolecular force, so it has to be between two different molecules. The negative end of one molecule is attracted to the positive end of a different molecule. A lot of students get this confused. When they see hydrogen bonding, they think of the covalent bond that connects an oxygen with a hydrogen in H2O. This is not hydrogen bonding. This is a covalent bond. It's an intramolecular interaction. The hydrogen bonding happens between two different molecules. So here again, with the dotted lines, the negative portion, the negative portion of one water molecule is attracted to the positive portion of a different water molecule. And you could see the same thing with ethanol, the hydrogen bonding that's happening there. Because hydrogen bonding is so much stronger than dipole-dipole and London dispersion forces, molecules that exhibit hydrogen bonding will have higher boiling points and melting points. But you have to remember, covalent bonds are the strongest out of these intermolecular forces. Okay, so again, when you're trying to boil or melt something, it's the intermolecular forces that are being broken, not the covalent bonds. Here we have a comparison between ethanol and dimethyl ether. They have the same molecular formula, so they have the same molar mass, but the structures are different. The atom connectivities are different. So these are considered isomers. Now take a look at the boiling points and melting points for these two. You can see that ethanol is much higher in boiling point and melting point compared to dimethyl ether because of the hydrogen bonding that ethanol can exhibit. So ethanol can exhibit hydrogen bonding, dipole-dipole, and London dispersion forces. Dimethyl ether can exhibit London dispersion and dipole-dipole. That's it. If we take a closer look at the Lewis structure, you can see that, yeah, there is an oxygen, there are hydrogens, but they are not directly bonded with the oxygen. Ethanol exhibits hydrogen bonding because the oxygen is directly bonded to a hydrogen. Let's take a look at the compounds that are formed with hydrogen and the elements found in groups 4A and 6A. We could see here in group 4A, as molar mass increases, the boiling point also increases. We could see that in part of group 6A, the anomaly here is water. And that's because water can exhibit hydrogen bonding and not just London dispersion and dipole-dipole. Here we have 3 compounds. One of them is liquid at room temperature. The other 2 are gases. So pause the video, figure out which one is liquid at room temperature and why. When you're ready for the answers, click play. Okay, so here are the molar masses for these 3 different compounds. You would think that they would all have about the same boiling points, melting points, but that's not true because the hydrogen peroxide can exhibit hydrogen bonding. So because that is an extra intermolecular force and because it's stronger than dipole-dipole and dispersion forces, it is a liquid at room temperature. The other 2 would be gases. All right, here's another question. Which has the higher boiling point, HF or HCl? Again, pause the video to figure it out. When you're ready for the answer, click play. Okay, so HF would have the higher boiling point. Yes, it's true that chlorine has a higher molar mass compared to fluorine, but HF exhibits hydrogen bonding. So that causes it to have a higher boiling point than HCl. The last type of intermolecular force is called ion dipole. And here we are very specific. Just think of a salt dissolved in water. So our salt here in this example is NaCl. It can dissolve in water because it can be broken up into anions and cations. We could see here one anion is being surrounded by water molecules, but those water molecules are arranged so that the hydrogens are facing towards the Cl-. Now with the cation, Na+, it's also surrounded by water molecules, but the oxygens are directed towards the Na+. So with this type of intermolecular force, it is very specific. You're dealing with ions being surrounded by a polar solvent. It doesn't have to be water. It can be any solvent that is polar. Here's a summary of the 4 different intermolecular forces. The first one that we looked at is dispersion, or London forces. Remember that they are found in all molecules and atoms. And the trend that you have to remember is that with increasing molar mass, we would have increasing polarizability, and so stronger dispersion forces. With dipole-dipole forces, you'll find that in polar molecules because they have a permanent dipole. In regards to pure substances, Hydrogen bonding is the strongest type of intermolecular force. And we can only see that in molecules that have fluorine, oxygen, and nitrogen, and they have to be directly bonded to a hydrogen. Ion dipole is the strongest type of interaction, but this deals with mixtures as opposed to pure substances. So if your mixture consists of ionic compounds with a polar solvent, then that mixture is going to exhibit ion dipole interactions. Let's test your understanding. Which substance has the highest boiling point? So pause the video, look at your three choices very carefully, and when you're ready for the answer, click play. Our answer here is letter A. All three of these substances exhibit dispersion forces. Letter B is a polar molecule, so it would also exhibit dipole-dipole. Letter A is also polar, so it'll exhibit dipole-dipole, but it would also exhibit hydrogen bonding because we have an oxygen that's directly bonded to a hydrogen. So letter A is the substance that would have the highest boiling point. From these pairs of compounds, you're going to figure out which ones form homogeneous solutions. So you're going to figure out which ones are miscible or mixable with each other so that they form homogeneous solutions. And for those that form solutions, figure out which types of forces are involved. So please pause the video, look at these pairs very carefully, figure everything out, and when you're ready for the answers, click play. Okay, so for letter A, our first pair, these two are immiscible. CCl4 is nonpolar, and we already know that water is a polar substance. So these two cannot mix, they are immiscible. Letter B, KCl can be dissolved in water, so these are miscible. And the type of intermolecular forces involved are all four. We have ion dipole because the KCl can be dissolved into K plus Cl minus. We have hydrogen bonding because of the water, dipole-dipole because of the water, and dispersion forces can be found in all molecules. The pair in letter C is considered miscible because both of them are nonpolar molecules and they only exhibit dispersion forces. Letter D, these two are miscible and we only see dispersion, dipole-dipole, and hydrogen bonding. We don't have any ions breaking up in these compounds. Besides melting points and boiling points, another manifestation of intermolecular forces is surface tension. So here we could see it with this insect just sitting on top of the water. It's not floating in the water, it really is just sitting on top of it. So the surface of the water is not breaking at all. So how is it that an insect like this, or even a dry leaf, can sit on top of the water? So when we see an object just sitting on top of the surface of a liquid, that liquid is trying to minimize its surface area. So if the object is light enough, then the surface of that liquid will not break. Surface tension is the energy needed to increase the surface area of a substance by a certain amount. So here we have water and benzene, and their surface tension values at room temperature. And based on these values, you should be able to say that water has stronger intermolecular forces compared to benzene. We know that water exhibits dispersion, dipole-dipole, and hydrogen bonding. But with benzene being a nonpolar molecule, it only exhibits dispersion forces. So we need less energy to break those forces and to spread out that benzene a certain amount. Let's take a look at water molecules at the surface and just below the surface. Here we have a surface molecule that only has 4 neighbors to stabilize it. An interior molecule has 6 neighbors to stabilize it with intermolecular forces. So going back to the chapter with potential energy, if a system has a lot of potential energy, then the less stable it is. So we can say that this interior molecule has less potential energy and is thus more stable. Now, let's see what happens when we try to spread out the water so that it'll have an increased surface area. Well, now this interior water molecule is going to have to be pushed up towards the surface. Now, what did we say about the molecules at the surface? They would have a higher potential energy and will thus be less stable. Well, this interior water molecule will not be happy there. It's satisfied where it is. It's very stable with its 6 neighbors, so it's not going to want to move. Also, taking a look at this surface molecule, we see that it has attractions towards molecules to the left and to the right of it, but the net pull is going to be downward because we see that there are 2 neighboring water molecules below it. So the same can be said with all the other surface molecules in water. They're going to be pulled downward. So this is what causes the tendency to minimize surface area and allow light objects just to sit on top of the water. So with that net pull towards the interior, the surface molecules act like skin. So something like a paperclip would just sit on top of the water. That surface tension would prevent any breakage in the surface. We already saw how strong intermolecular forces will increase the surface tension. Water has the hydrogen bonding along with dipole-dipole interactions. Benzene only had the dispersion forces, so it takes more energy to spread out water compared to benzene. Taking a look at temperature, if temperature is raised, then surface tension is decreased. When you raise the temperature of a liquid in this case, the molecules will move a lot more because they'll gain kinetic energy. So some of those intermolecular forces are going to be disrupted. So then it'll be easier to spread out that liquid across the surface. Viscosity is another manifestation of intermolecular forces, and that is the resistance of a liquid to flow. So some examples would be motor oil, or molasses or pancake syrup. They don't flow as easily as, let's say, water or acetone or methanol. The trend that you have to look out for is the number of intermolecular attractions. If this number gets larger and larger, then the viscosity gets higher and higher. So we could see that with the list of hydrocarbons here. Again, we have pentane all the way through nonane. And we could see that they're all straight chains. As the molar mass increases, the viscosity would also increase. So just think of something like nonane being tangled upon itself. These chains are so long that they tumble through each other as the liquid is flowing. So the more carbon chains there are, the higher the viscosity would be. And that's going to be true with any type of molecule. So the more spherical the shape, the lower the viscosity of the liquid will be. And that's because those molecules won't be tangled up on itself, and there would be less surface-to-surface interactions. Here we have our two isomers, N-pentane and neopentane. So with the N-pentane, picture two pieces of paper stuck together. With neopentane, two spherical balls that are in contact with each other. So with N-pentane, think of this having an infinite number of contact points for attraction. So these molecules will be sticking together a lot. Also, straight chain molecules like this will be tangled among themselves. So N-pentane would be more viscous compared to neopentane. Here we would see a smaller area for interaction, smaller area for attraction, and because it's spherical, the molecules won't be tangled among themselves. Another factor that would affect viscosity is temperature. So if we increase the temperature of a substance, the molecules in that substance would have a higher average kinetic energy, and that'll cause the molecules to move more. So when that happens, if there's enough kinetic energy, then intermolecular attractions could be overcome. So that means that the liquid would move more freely, so the viscosity would decrease as the temperature increases. When you introduce a capillary tube to a liquid, you'll see that liquid flow up that tube, and that is capillary action. So there are two forces at work here, adhesive and cohesive. With adhesive forces, the liquid molecules would be attracted to the tube surface. Cohesive forces, the liquid molecules are attracted to each other. We can see here that the narrower the tube, the higher the liquid will go, and the height of that liquid depends on the diameter of the tube and gravity. But in any case, we could see that adhesive forces are pulling the liquid up the inside of the tube, and at the same time, cohesive forces are pulling more liquid molecules so that we don't have a hollow tube that's just coated with liquid molecules. That tube is going to be filled with liquid molecules. I'm sure by now you've all read a graduated cylinder that's filled with water. You know to read it at eye level, and you know to read it at the meniscus. And the meniscus is the curved portion of the liquid surface And the reason why it's curved is because there is competition between adhesive and cohesive forces. Now, the shape of the curve and even the degree of the curve depends on the liquid substance and the material of the container that it's in. So here on the left-hand side, we have water inside a glass test tube. And it's a little bit hard to see here, but the meniscus is concave. And that is because the water has a stronger attraction to the glass tube than to itself. So again, here, the adhesive forces are stronger than the cohesive forces. So that's why we have a concave meniscus, and we always read the meniscus at the curve. So the curve is at the bottom here. Now on the right-hand side, we have mercury. The meniscus here is convex. And that's because the cohesive forces are stronger here than the adhesive forces to the glass tubing. Again, if this was in a graduated cylinder or even a thermometer, you would still read it at the meniscus, at the curve, but the curve is at the top of the liquid. Before we go into the energetics of vaporization, you have to understand average kinetic energy. So we already know that the molecules in a solid don't move around, but they do vibrate. Molecules in a liquid not only vibrate, but they can also rotate. They can freely move around. Now, average kinetic energy is proportional to temperature. So as we raise the temperature of a substance, the average kinetic energy will also be raised. Now, think about your average in a class based on exam grades. Some of your exam grades could be low, some could be high, but in the end, if you have a passing grade, then you can move on to the next course. The same thing goes with these molecules. Some molecules will have a higher kinetic energy than others. And it's these molecules that have the higher kinetic energy, they're the ones that can escape into the gaseous phase. So these liquid molecules that have high kinetic energy can be found anywhere in the liquid. It's just that when they're at the surface, they're more likely to become gaseous molecules. So the larger the surface area, the faster the rate of evaporation. We can see here that as we increase the temperature of the substance, then more molecules will have enough minimum kinetic energy to escape as gaseous molecules. They'll have enough energy to overcome those intermolecular attractions and become gaseous molecules. So the higher the temperature the substance has, the faster the rate of evaporation. The opposite process of vaporization is condensation. So that's when gaseous molecules collide with each other and form liquid molecules again. If you ever had to boil water as you're cooking, you'd cover up the pot. When you know that the water is boiling and you lift off the lid, you see water droplets on the inside of the lid. So that's condensation. So when that happens, the water vapor would lose energy from colliding with each other, and they would form less energetic liquid molecules. So if we keep that pot of boiling water covered, ideally speaking, you won't lose any H2O molecules, whether it's liquid or vapor. At some point, the rates of vaporization and condensation will become equal. So we would reach a level of equilibrium. Now, if you are boiling that pot of water without the cover, then the vapor molecules can escape. They're less likely to collide with each other and condense back as liquid water molecules. So then what's going to happen? Eventually, you won't have any more water to boil in the pot. You've lost all your liquid. So the rate of vaporization would be greater than the rate of condensation. For those with weaker intermolecular forces, they're the ones that are going to have the lower boiling points, and so they're the ones that are going to evaporate the fastest. So here we have dimethyl ether and ethanol. They have the same chemical formula, same molar mass, they are isomers. Ethanol is the one that has hydrogen bonding, which is stronger than dipole-dipole and dispersion forces. Dimethyl ether only has those two. It does not have hydrogen bonding. So because of that, dimethyl ether will have the lower boiling point, and so because of that, it'll have the faster rate of evaporation. Volatile liquids are the ones that can evaporate very easily. So you could smell them from far away. Classic examples are gasoline and acetone, the active ingredient in nail polish remover. Those that do not evaporate easily are called non-volatile liquids. So make sure you have these relationships down when you're trying to figure out the rate of vaporization of a substance. If you want to increase the rate of vaporization, you'd first have to increase the temperature. Doing so would increase the average kinetic energy of all those molecules. So the more likely those high energy molecules will escape as gaseous molecules. If we increase the surface area, then we'll also increase the rate of vaporization. So just picture a glass of water and some spilled water on a table. Well, that spilled water is going to dry up faster because of the increased surface area. The rate of vaporization there will be higher. The next thing, we have to take a look at the intermolecular force strength that's involved in whatever substance that we're looking at. If we have something like water, it has dispersion, dipole-dipole, and hydrogen bonding. That will have a lower rate of vaporization compared to something like acetone, which only has dispersion and dipole-dipole. And the last thing, it's not on this slide, if everything else is the same, then take a look at molar mass. Those with smaller molar masses will have a higher rate of vaporization. Let's check for understanding. Out of these four options, which one has the greatest rate of vaporization? So pause the video so that you could read the four options very carefully. Pick your choice, and when you're ready for the answer, click play. Okay, so the answer here is letter D. We want to pick the sample that has the higher temperature. Because remember, the higher the temperature, the higher the average kinetic energy of the molecules. So then the more likely those molecules will escape as water vapor. So that's how we eliminate choices A and C. Now we're picking choice D because this one has a beaker with a 7-centimeter diameter. That allows the water to have more surface area. If it was less, like in choice B, then those high energy water molecules won't be able to escape as water vapor. So if we have a larger diameter, the water would have more surface area, and the more likely those high energy water molecules will be able to escape as water vapor. Here we have 3 pairs of compounds. You need to pick the one with the higher vapor pressure at a given temperature. So please pause the video, pick your choice, make sure that you have your reasoning ready, and when you're ready for the answers, click play. Okay, so for a problem like this, make sure that you have the relationships written out. So if a substance has weak intermolecular forces, then not too much energy is needed to overcome those forces. So if we're working with a liquid and we're trying to boil it to a gas, that boiling point will be very low. And because the boiling point is low, a lot of the liquid molecules would have enough energy to become vapor, to become gaseous. So because of that, we would see high vapor pressure for very volatile substances. So for letter A, methane is the one that's going to have the higher vapor pressure. It's the one that's nonpolar and it has a smaller molar mass. With methanol, it has a smaller molar mass than propanol, but both exhibit hydrogen bonding. Okay, so if the intermolecular forces are the same in both substances in the pair, then you have to take a look at molar mass. Then finally, formaldehyde is the one in letter C that'll have the higher vapor pressure. Okay, so it's important to note the structure here. Yes, it does have an oxygen. It also has a couple of hydrogens, but there is no hydrogen bonding here because there is no hydrogen directly bonded to this oxygen. So this molecule here only exhibits dispersion forces and dipole-dipole. So formaldehyde is the one that has the higher vapor pressure. In vaporization, let's take a look at what happens to the molecules in terms of energy. So when liquid molecules escape as gaseous molecules, it lowers the average kinetic energy. So just think that you're taking a class and your average is based off of 3 exam grades, and your scores are 90, 95, and 100. So your average test score is 95. Now let's say that your teacher wants to throw away the test where you scored a 100 because for some reason that test is invalid. So now what test scores are going to be counted? The 90 and the 95. What's your average now? Well, it decreased to a 92.5. This is the same idea when gaseous molecules don't condense back into the liquid. The average kinetic energy would be lowered. Now, what does that mean in terms of temperature? Well, the temperature would also decrease. That heat, the high energy molecules that contain a lot of heat, they're not coming back down to the liquid. So that's what's happening with vaporization. As liquid molecules are becoming gas molecules, heat is being taken away. This is an endothermic process. So in order for liquid molecules to overcome the intermolecular attractions, heat is needed to break those attractions so that liquid molecules can become gaseous molecules. So the heat of vaporization is also called the enthalpy of vaporization because we have delta H here. And that's the amount of heat required to vaporize 1 mole of a liquid. So here you can see in the table that our unit is most likely going to be kilojoules per mole. Now, if you have this delta H value, delta H vaporization, then you'd know delta H condensation. It's going to be the same magnitude, but opposite in sign, because these two processes are opposites. Okay, so let's take a closer look at table 12.7. Here we have 4 different liquids, and just by looking at the boiling points for these liquids, we could tell which one would have the stronger intermolecular forces. And that's going to be water, because it has the highest boiling point in the bunch. The diethyl ether, we've seen this before, this diethyl ether only has dispersion forces, so it's going to have the lowest boiling point in the group. Okay, so now back to delta H vaporization. This value is temperature dependent. So let's take a look at water. The delta H vaporization value at boiling point. So at 100 degrees Celsius, this delta H value is 40.7 kilojoules per mole. Now, if we lowered the temperature down to 25 degrees Celsius, we see that we have a different delta H value now. It's 44.0 kilojoules per mole. And that should make sense, because 100 degrees Celsius, it feels hotter than 25 degrees Celsius. So if we're at a cooler temperature, then we're going to be working with a higher delta H vaporization value. Let's take a look at a typical problem dealing with delta H vaporization. Here we have to calculate the mass of water in grams that can be vaporized at its boiling point with 155 kilojoules of heat. So we're going to need one of the values from table 12.7 to figure all this out. And really what this is unit conversions. Here we go. This is it. We take what we started off with. So we have 155 kilojoules, and we need to figure out how much water can be vaporized with this amount of energy. So here's our first conversion factor. 1 mole of H2O is going to equal 40.7 kilojoules. This again comes from table 12.7. But specifically, we're going to be looking at the boiling point of water. So that's why we're using this conversion factor. At this point, we have moles of H2O. So now we got to convert that to grams of H2O using the molar mass of water. And after we multiply and divide everything in our calculator, we get 68.6 grams of H2O. And that's it. Here's another one. How about you guys try this out? Calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. So pause the video, work this out. It is very similar to the first one, but this time you're working backwards. Work it out, and when you're ready for the answer, click play. Okay, so here's your setup. You're starting off with the kilograms of water. Then you got to convert it to grams, so multiply by 1,000. Then you have to convert grams of H2O to moles of H2O. Then use the same conversion factor as before, but this time you flip the numerator and denominator so that you get 5,827 kilojoules. Here's a more complicated word problem, but you've seen this type of problem before when we're working with thermochemistry. So here we have 0.48 grams of water at 25 degrees Celsius, and it condenses on the surface of a 55-gram block of aluminum that is initially 25 degrees Celsius. If the heat released during condensation goes only towards heating the metal, what is the final temperature of the metal block? Okay, so hopefully you have some equations in mind. Let's start off with what we just did in the last two problems. We have grams of water. We're converting that to moles of water. Now here's our conversion factor, going from moles of water to kilojoules. Now here's a new value. This still comes from table 12.7. This is a new value because we're not at 100 degrees Celsius. We're not at the boiling point like in the last two problems. We're at 25 degrees Celsius now. And now all of a sudden we have a negative value. Why do we have a negative value? Because our process is condensation, not vaporization. So there are keywords that you have to look out for so that you use the right values and the right signs. So when you work all this out, we have negative 1.17203 kilojoules. And this is our Q water. This is the heat of the water. Now, because heat is being transferred from one object to another, we have to use our relationship here. Q aluminum is equal to negative Q water. This is our heat transfer relationship. So hopefully you guys didn't forget Q equals MCAT. We have to figure out the final temperature of the aluminum block. We have all the other variables, so we'll plug that in. We had as the heat in kilojoules, don't forget to convert that to joules, because our specific heat capacity for aluminum has joules in the unit. Okay, so we're solving for final temperature. We do the algebra for that, and our final answer is 48.6 degrees Celsius. Now think back to that pot of boiling water that you covered up with a lid. If that pot is sealed well enough, then no water molecules or water vapor are going to escape from that pot. Okay, so evaporation and condensation are going to happen at the same time inside that pot. Remember that they're opposite processes, but at some point the rates of vaporization and condensation will become equal, and that's what's called dynamic equilibrium. Now you could have different amounts of liquid and water vapor, like let's say, I don't know, like 100 milliliters of liquid water, but then 10 milliliters of water vapor. We can have that as long as the rates of vaporization and condensation are the same. So in picture A, we see that there are no water vapor molecules inside this flask. So the rate of vaporization here is going to be very high. Now part B, we already have some water vapor, so the rate of vaporization is going to slow down a bit. We're also seeing that some of these water vapor molecules are condensing back down to the liquid. Now part C, this is where dynamic equilibrium is happening. The rate of evaporation is going to equal the rate of condensation. So remember, the key phrase that you have to remember with dynamic equilibrium is same rates. So same rate of evaporation, same rate of condensation. We can have 100 mLs of water and 10 mLs of water vapor. That's fine. It's just that at dynamic equilibrium, these amounts are going to be changing by equal amounts because the rates of vaporization and condensation will be the same. Now think back to the chapter with the different gas laws and the ideal gas law. Any vapor exerts a certain amount of pressure on the inside walls of the container that it's in and on the liquid that's below it. So, which liquids exert a lot of vapor pressure? Well, they're going to be the ones that are more volatile. So think of acetone or gasoline. They're the ones that are going to have the weaker attractive forces. So just dispersion forces, or maybe just dipole-dipole. The more volatile the liquid, the more vapor pressure it's going to exert. Why? Because more molecules will be able to escape into the gaseous phase as vapor. Now say that we have a sealed flask with liquid and its vapor, and it's also at dynamic equilibrium. Now, what happens if the volume of this chamber is increased? Well, now those vapor molecules can't maintain the same pressure with this new volume. There's not enough vapor molecules to hit the inside walls of the chamber to maintain the pressure. So now what's going to happen? The rate of condensation is going to slow down, and the rate of vaporization is going to go up, so that more vapor molecules will be created, and in doing so, the vapor pressure inside the chamber will rise up to what it was before. Once we have the vapor pressure from before, then the rate of condensation will increase, the rate of vaporization would decrease, so that we're now back at dynamic equilibrium. So picture A shows a chamber filled with, looks like some kind of hydrocarbon in liquid form and vapor form. Now this is what happens when the volume is increased. There's not enough vapor molecules to hit the inside walls of this chamber to maintain the vapor pressure. So the rate of vaporization is going to have to increase to compensate. Then at some point, dynamic equilibrium will be established again. Now what happens when the volume is decreased? Now there's too many vapor molecules above the liquid, so the rate of condensation is going to increase, the rate of vaporization is going to decrease a bit. So when more gas molecules condense, at some point, dynamic equilibrium is going to be reestablished. In a later chapter, you're going to take a closer look at this concept, Le Chatelier's principle. And that's basically what we just saw in changes in dynamic equilibrium. The system is going to change so that it would reduce the effects of that change. Let's check for understanding. What happens to the vapor pressure of a substance when its surface area is increased at constant temperature? So pause the video, read your answer choices very carefully, and when you're ready for the answer, click play. The answer here is B, the vapor pressure remains the same. So if we have a beaker that has a larger diameter, then the rates of vaporization and condensation would be higher compared to what we find here in the beaker with the smaller diameter. But these rates have nothing to do with vapor pressure. Now, we've already seen what happens when temperature increases in a system. So think about a solid melting or liquid boiling. Those intermolecular forces that hold the molecules together would be overcome. So then what's going to happen to the vapor pressure when a liquid is being turned into a gas? Well, that vapor pressure is going to increase as temperature increases. Now, if those intermolecular forces are very strong, like we see in water, then a lot more energy is needed to overcome those intermolecular forces. So for something like water, the boiling point is going to be very high compared to acetone. Speaking of boiling point, it is the temperature at which the vapor pressure equals the external pressure. So now let's say that this pot of water is boiling at sea level. Well, at sea level, the external pressure is 1 atmosphere. So what can you say about the vapor pressure inside this pot? It's also 1 atm. Now it gets very interesting when the external pressure is not 1 atm. If you take a look at table 12.7 again, there's a column that's labeled normal boiling point, which is the temperature at which the vapor pressure of the liquid is 1 atm. In other words, those liquids in table 12.7 were boiling at sea level. So then what happens when we try to boil something like water at different altitudes? Well, now we're going to have different boiling points because the pressure, the external pressure, is going to decrease as the altitude increases. The air gets thinner as we go higher in altitude. So if you're at Mount Whitney and you are trying to cook something through boiling water, yeah, you could still boil water, but it'll be at 87 degrees Celsius. That might not be enough heat to actually cook the food that you want to eat. Here are some vapor pressure curves for diethyl ether, ethanol, water, and ethylene glycol. We're only going to focus on these three because we could see what their normal boiling points are in this graph. Now, if you had no idea what the Lewis structures were for these three compounds, you should be able to figure it out based on the boiling points that are given here. So for diethyl ether, it has the smallest, the lowest boiling point of 34.6 degrees Celsius. So this should tell us that it should exhibit weak intermolecular forces. Water has the highest at 100 degrees Celsius, so it should exhibit the strongest type of intermolecular force. Okay, so now let's take a look at these three Lewis structures. We can see that they are polar because they all have oxygens with some degree of polarity. Letter A can exhibit hydrogen bonding because we have an oxygen connected to a hydrogen. In fact, there are two of them. We don't see hydrogen bonding here for letter B. We could see hydrogen bonding for C. Okay, so just based on this quick overview, letter B should be the diethyl ether. Now we're down to ethanol and water. Okay, so both of these, A and C, can exhibit hydrogen bonding, but with letter A, we can see that it can bond twice Why? Because it has two hydrogens directly bonded to an oxygen. So if we have another H2O molecule here on this end and another one on this end, we can form two hydrogen bonds. But over here, if we have another molecule like this, we can only form one hydrogen bond. So even though A and C can exhibit hydrogen bonding, letter C only forms one hydrogen bond onto itself. So this must be ethanol, letter C, and letter A is water. So using the same graph, estimate the boiling point of water at an external pressure of 200 torr. So pause the video, make sure you read this graph properly, and when you're ready for the answer, click play. Okay, so the answer here is letter A, 66 degrees Celsius. So here's our 200 torr. We're going to go straight across until we hit water, which is right here. Okay, now we're going to go down to the x-axis so we can figure out what temperature that is. All right, so it's between 60 and 80. We didn't quite reach the halfway point, so it's got to be less than 70. So our only answer choice that would make sense is letter A. So looking at those vapor pressure curves, we can safely say that as we increase the temperature, the vapor pressure would also increase. But here's the thing, the relationship between those two variables is not linear. So it's really hard for scientists to compare those two variables and even other liquid substances when the relationship is not linear. So we'd have to use an equation like this, the Clausius-Clapeyron Equation, to make these two variables linearly related. So we could see here, this equation looks very much like the equation for a line. Okay, here's our y-axis, x-axis. So our y-intercept is the natural log of the vapor pressure. Our slope is the negative delta H vaporization over R. Now the R that we're going to use is this value, 8.314 joules per mole K. This is different from the R value that you used in the gas chapter. And you have to be careful with the units for delta H. Sometimes you would see it at kilojoules per mole, other times you'd see it at joules per mole. So you might have to do some unit conversion there. The version of the Clausius-Clapeyron equation that you're going to be using more often is the two-point form. Now this is not going to be as precise as the other linear form, but it is easier to use. So basically you're going to be given two different scenarios of different temperatures and pressures, and you would have to solve whichever variable is unknown. Now one thing that you have to remember, if normal boiling point is mentioned, you have to remember 1 atm or 760 torr or 760 millimeters of mercury. Okay, whatever variable that they give you. In this problem here, you're asked to determine the heat of vaporization of dichloromethane based on these results. So really the only way for you to figure this out is to use Excel. Plug in these values, get a line of best fit with an equation, and then use the slope that they give you to figure out the heat of vaporization. Okay, so don't forget that slope is negative delta H vaporization over R. So we manipulate this equation a little bit so that we could solve for delta H. We plug in our values, and our delta H value is 31.4 kilojoules per mole. Now again, you're not going to be using this form of the Clausius-Clapeyron equation, but I want to just show you how it's used and how you would solve a problem like this. Now you're going to be using the 2-point form of this equation. Here we have methanol with a normal boiling point of 64.6 degrees Celsius and a heat of vaporization of 35.2 kilojoules per mole. What is the vapor pressure of methanol at 12 degrees Celsius? So please pause the video, work everything out, and when you're ready for the answer, click play. Okay, so there's a lot of variables in this equation, so you should write everything out. Whatever's given to you and your unknown that you're solving for. Okay, so here we're trying to figure out the vapor pressure in our second scenario. And here is our equation that we're going to use. Again, we're trying to find P2. Okay, so our temperatures were given in Celsius, so you're going to have to convert to Kelvin. We plug in our values. Okay, our delta H value was given in kilojoules per mole, so we have to convert that to joules to match up the units in our R value. So after carefully plugging all these numbers in the calculator, we have ln of P2 over P1 equal to negative 2.31. Now to get rid of the natural log, we're going to have to set both sides to the base E. And that's how you get rid of the natural log on the left-hand side. Then all you have to do is multiply both sides by P1 to isolate P2. Plug in the rest of the values. So in the end we have 75.4 torr as our P2. And yes, this should make sense because at a lower temperature we would expect a lower vapor pressure. Here we have propane with a normal boiling point of negative 42.0 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What is the vapor pressure of propane at 25 degrees Celsius? So please pause the video, work this out, and when you're ready for the answer, click play. So here's our Clausius-Clapeyron equation, 2-point form. We plug in our values, making sure that we convert our kilojoules to joules, just to match up our units. Okay, so now we have natural log of P2 over P1 equal to 2.226399. In order to get rid of the natural log, we have to set both sides of the equation to the base E. We multiply both sides by P1 so that we could isolate P2 on one side. And don't forget, because the question says normal boiling point, our first scenario is at 1 atm. So our final answer is 9.3 atm. And that should make sense because our temperature in the second scenario increased. So our pressure in the second scenario should also increase. So far, when we were looking at vaporization, we were looking at a liquid in a sealed container without heating it. Now what would happen when we heat that container? Well, we end up with something called a supercritical fluid. Now let's look at these pictures so that you could understand how a supercritical fluid is produced. So in this sealed chamber, we have some liquid and it's vapor above it. Now we're going to increase the temperature of this chamber. As the temperature increases, more vapor is being produced, so the vapor pressure is increasing here. We're going to keep on increasing the temperature. Now the density of the gas is going to increase because we're making more vapor, and the volume of this container stays constant. So the density of the gas is going to increase. At the same time, the density of the liquid will decrease. At some point, this meniscus is going to disappear, and at a certain temperature and pressure, we end up with what's called a supercritical fluid. So it's like a hybrid of a gas and a liquid. Okay, so the supercritical fluid can effuse through solids like a gas. It could dissolve materials like a liquid. Supercritical carbon dioxide is actually used to extract caffeine from coffee beans. So this type of phase is very important. We're not going to get fancy with these glossary terms here. The temperature and pressure where a critical fluid is created are called critical temperature and critical pressure. Now think back to how a gas can turn into a liquid. Well, we could change the temperature. We could lower the temperature of the gas so that it turns into a liquid, or we can increase the pressure. But if we reach the critical temperature of a substance, it doesn't matter how big the pressure is. There's no way for that gas to turn into a liquid. Two other interesting processes are sublimation and deposition. Sublimation is where a solid turns directly into a gas, and deposition is where a gas turns directly into a solid. There is no liquid phase in any of these processes. So because of that, when we're thinking about sublimation or deposition, we can say that molecular solids have vapor pressure. Also, don't forget, when we're going from solid straight to gas, that is an endothermic process, because you're going from particles that are not as energetic into particles that are very energetic. So you need to add energy to do that. And then going from gas to solid, deposition is an exothermic process. Now we'll take a look at melting, also known as fusion, and this is an endothermic process. In the next several slides, you'll see many similarities with vaporization, which is again another endothermic process. So as temperature increases, the solid molecules are gaining energy to overcome the intermolecular forces that are holding them in place. And so the molecules that have gained enough energy can now flow as liquid molecules. Now the opposite of melting is freezing, but in your textbook you might see the term crystallization. So think of the crystal lattice, or the crystal structure that forms as liquid water freezes to ice. If liquid molecules don't get turned back to solid molecules, then the average kinetic energy of the system decreases. It's like that example with the teacher who throws away a test where you scored 100 and you're only left with scores of 90 and 95. So that lowers your test average. It's the same idea here. So if the average kinetic energy becomes lower, then the temperature also lowers. Now let's take a look at heat of fusion, or enthalpy of fusion. And that's the amount of heat needed to melt 1 mole of the solid. So if we take a look at our units here, it is in kilojoules per mole. And we already said that fusion is the opposite of freezing or crystallization. So if you have this delta H value, delta H fusion, and you know you're dealing with crystallization or freezing, you are going to use the same numerical value, but opposite in sign. Okay, so now let's take a look at heat of sublimation. Remember that sublimation, we're going from a solid straight to a gas. So thinking back to Hess's law, where we're adding delta H values and reactions together, fusion is melting. So that's going from solid to liquid. Vaporization, we're going from liquid to gas. So when we're adding these two processes together, these two delta H's together, we come up with sublimation. Here we have 4 different compounds with the delta H fusion and delta H vaporization values. Now, why is it that the heat of vaporization for all 4 of these compounds is higher than that of fusion? Well, think of what happens when we try to melt a solid. Melting requires that intermolecular forces be only partially overcome. Now think about vaporizing a liquid to a gas. Those intermolecular forces have to be completely overcome. Remember that a gas is mainly empty space. Those gas molecules won't really come in contact with each other. Once in a while, they'll collide with each other, maybe form back to a liquid, but for the most part, they are going to be spread out in a given amount of space. So for vaporization to happen, those intermolecular forces that are present have to be completely overcome. That's why delta H vaporization is higher than fusion. Now let's figure out how to calculate the heat needed to melt a solid. And here we're going to use H2O as our example. So we're starting off with solid ice at -10 degrees Celsius. And then we're going to heat it up to liquid water at around 35 degrees Celsius. So starting off, as we add heat, we still have solid H2O, we still have ice, and we're going to stop right here until we get to the melting point of ice at 0 degrees Celsius. So for us to figure out the amount of heat that was added, we need to use Q equals MCAT. Now this should make sense because we see a temperature change. If you see a line with a positive slope in this case, because we're adding heat, then you're going to be using Q equals MCAT. We're still working with a solid. It's just that here the solid is increasing in temperature. Now, what happens after we hit the melting point? Now that solid is turning into a liquid. Heat is still being added. We could see that in the graph. But take a look, the temperature is not changing. So we cannot use Q equals MCAT here. That wouldn't make any sense because then we'd end up with Q equaling 0. And we see from the graph, Q has to be a positive number. So instead of Q equals MCAT, we're going to use Q equal to moles, so in this case moles of H2O, times heat of fusion. Okay, so again, heat is being added, but it's being used to overcome some of the intermolecular forces so that the solid can melt to a liquid. So when you see a line that has a 0 slope, you're looking at a phase change. Now what happens when all the solid turns into the liquid? Now the liquid will have a change in temperature again. So this is where you would use Q equals MCAT. Now the same can be said when we're trying to vaporize a liquid. So here in this first segment, we have liquid water, and it's increasing in temperature. And we're going to stop right here at the boiling point of water. So now, which equation are you going to use to figure out how much heat was added? You're going to use Q equals MCAT because we have a temperature change. Once we're at the boiling point, so 100 degrees Celsius, we're still adding heat, but there is no temperature change. So we're going to use Q equals the number of moles times heat of vaporization this time, because now we have a liquid turning into a gas. And again, the heat that's being added is not going to increase the temperature, but it's going to be used to overcome the intermolecular forces found in the liquid so that that liquid can turn into a gas. So now this last segment here, the one with the positive slope, all of this is now water vapor, and that water vapor is now increasing in temperature. So this is where we would use Q equals MCAT again. So if you were given the question, how much heat is needed to warm 1 mole of H2O from negative 25 degrees Celsius to 125 degrees Celsius, you would need to figure out the Q values for these 5 segments. So for segment 1, our line with a positive slope, the ice is being heated up from negative 25 degrees Celsius to 0 degrees Celsius. So we're going to need to use Q equals MCAT. We can figure out the mass of 1 mole of ice. And this value right here is the specific heat of ice. So be careful there. This is the specific heat of ice. Plug in your values so that you get 0.941 kilojoules. Our second segment is our first phase change. So the slope of this line is 0. We're not going to use Q equals MCAT because we don't have a change in temperature. So instead, we're going to use Q equals to moles times delta H fusion. And here's the value for fusion. Just multiply those two numbers together to get 6.02 kilojoules. Segment 3 is another line with a positive slope. So we have a change in temperature. At this point, all of the solid has been converted to liquid. So now the temperature of that liquid is going to change. So we're starting from 0 degrees Celsius to 100 degrees Celsius. We're going to use Q equals MCAT. Now here's a value that looks familiar. It's the specific heat of water. When we plug in our values, we get 7.52 kilojoules. Our next segment is another horizontal line. So there is no temperature change because all of the liquid water is turning into water vapor. So we're going to use the number of moles of H2O times the heat of vaporization this time. So we come up with 40.7 kilojoules. Our last segment is another line with a positive slope. So now we have a temperature change. All of our liquid has turned into gas. It started off at 100 degrees Celsius and will end at 125 degrees Celsius. So we're going to use Q equals MCAT. Here's the specific heat for steam. After we plug in our values, we get 0.904 kilojoules. So let's answer this question now. How much heat is needed to warm 1 mole of H2O from negative 25 degrees Celsius to 125 degrees Celsius? Well, we're going to add up all the Q values from our 5 segments so that we get 56.1 kilojoules. Now let's test for understanding. Here what's given to you is the specific heat for ice and the heat of fusion for ice. You have a small ice cube at negative 10 degrees Celsius and it's put into a cup of water at room temperature. Which of the following plays a greater role in cooling the liquid water? The warming of the ice from negative 10 degrees Celsius to 0 degrees Celsius, or the melting of the ice? Now pause the video. You have 2 equations that you could use to work this out. You might have to make an assumption to figure out the answer. When you're ready, click play. The answer here is letter B, the melting of the ice. So let me show you one way of working out this problem. Okay, so looking at the answer choices, you should be able to figure out which Q equation to use. So for letter A, we see a temperature change, so we're going to need Q equals MCAT here. Melting of the ice, that's a phase change, so that's Q equals moles times delta H fusion. Now we don't have mass or moles here, so this is where you need to make an assumption. So assume that you have 1 gram of H2O. You have 1 gram of ice. Okay? So to figure out the Q for letter A, you're going to be using Q equals MCAT. So we have a value of 20.9 joules. Now for letter B, you have to figure out how many moles there are in 1 gram of H2O. And then you have to multiply by the heat of fusion. Okay, when you do that, we would have a value of 334 joules. So this is how we get B as our answer. Now we're going to take a look at phase diagrams, which tell you where phase changes occur and the conditions needed for those changes. So for the most part, you're going to see in a phase diagram 3 different regions. And each of these regions represent solid, liquid, and gas states. There are also going to be lines that separate out these regions. And these lines represent the different boiling and melting points at certain pressures. So if you take a look at the liquid and gas sections, the line that separates them is called the vapor pressure curve. Now along this curve, both the liquid and the gas states exist in equilibrium. And that's going to be true for every other type of curve in a phase diagram. There's going to be one point in a phase diagram where all three lines intersect. And this is called the triple point. Here, at a certain temperature and pressure, all three states, solid, liquid, and gas, will exist in equilibrium. Here we have the phase diagram for water. Pressure is our y-axis, temperature is our x-axis. You need to note that most likely these two axes are not going to be to scale. So be very careful when you're reading any phase diagram. So you could see our three different phases, solid, liquid, and gas. We have our supercritical fluid at a really high temperature and a really high pressure. Okay, we see our three lines separating out the three different phases, and we have our triple point where the three lines intersect. Okay, so now when you take a look at this fusion curve, for example, along this curve we can say that the solid and liquid phases are at equilibrium. Same thing for the sublimation curve. The solid and the gas phase along this line, they are in equilibrium. Now, another piece of information that you could figure out from here is figuring out which phase is more dense, the solid or the liquid. Okay, and you do that by starting off at the triple point. What we're going to do now is increase the pressure. So we're going to move up in the phase diagram. We're just going to go straight up in a vertical line. Now, if you were going to do this in real life, if you increase the pressure of a substance, it's going to turn into the more dense phase. So that's what we're going to do here in the phase diagram. We're just going to go up, straight up. All right, now what phase are we in? We're in the liquid phase. So the liquid is more dense than the solid. And we know that that's true based on the table that we saw in the beginning of this video. Okay. Also, using this phase diagram, you can figure out which processes are endothermic and which ones are exothermic. So let's start off on this end of the phase diagram. We're at a negative temperature, so we're working with ice here. Let's just say that we're at negative 50 degrees Celsius. And now we're going to have to move towards the right. So what are we doing? We're increasing the temperature. So we're doing something that's endothermic, right? We're adding heat. Okay, so we're going from solid to liquid. Well, that's melting. That's fusion. So fusion is an endothermic reaction. Okay, let's keep going. We're in the liquid phase. We're going to keep adding heat. So we're still going in the endothermic direction. We're going now from liquid to gas. So we're going through vaporization. Vaporization is an endothermic reaction. Okay, so now let's go backwards, but let's start at a lower pressure. We're in the gas phase, right? So we're decreasing the temperature, we're taking away heat, so that's exothermic. We're taking away heat from the system, so now we're going from gas to solid. Okay, so you have to be careful here. That's not sublimation, that is deposition. So these processes that are labeled here, these are endothermic processes going from left to right in this phase diagram. Now let's combine what we know about the heating curve of water and the phase diagram of water. we're going to incorporate the 5 different segments here onto the phase diagram. So our first segment, the ice cube is being heated from -25 degrees to 0 degrees. Okay, so that's why we're here in the solid phase. Once we hit the melting point, now the solid is being turned into a liquid. So that's this fusion curve here. After all of the solid has been turned into the liquid, now we're at segment 3. The liquid is now changing temperature. So here we go. We got a long journey here. We're increasing temperature. We're still in the liquid phase. Oh, now what temperature did we hit? 100 degrees Celsius. Okay, so now we've reached the boiling point. Now the liquid is going to turn into a gas. So again, heat is still being added, but it's being used to overcome the intermolecular forces. Once we've done that, we've passed the vaporization curve. So now we're at segment 5. Our water vapor is now going to change temperature, going from 100 degrees to 125 degrees. So here we are, going from 100 degrees to 125. Here are a couple of phase diagrams of other compounds. You could see how similar they are to the water. The phases are arranged very similarly. So the solid would be towards the left-hand side of the diagram with the colder temperatures. Gases would be on the right-hand side with the higher temperatures and also lower pressures. Okay, you could see that both axes in both diagrams are not to scale. So taking a look at the one with iodine, we could see 0.118 atm pointed out. Then going up a little bit, we have 1 atm. And then all of a sudden we have 100 atm. Okay, so be very careful when you're reading a phase diagram. You could also still figure out which phase, solid or liquid, is the denser phase. So looking at iodine, we'll start at the triple point and we'll increase the pressure just by going up vertically. We see that the solid is denser than the liquid. Let's try this one out. We have a substance that has a triple point at -24.5 degrees Celsius and 225 millimeters of mercury. What's going to happen to a solid sample of this substance as it's warmed from -35 degrees Celsius to 0 degrees Celsius at 220 millimeters of mercury? So pause the video, see if you could draw out a basic phase diagram for this substance. When you're ready for the answer, click play. The answer is B, the solid sublimes into a gas. So let's take a look at a phase diagram and see how we could figure this out. Here's our triple point at -24.5 degrees Celsius and 225 millimeters of mercury. So it says that we're going to start off at a pressure of 220 millimeters of mercury. So we're just going to go a little bit lower here. And the substance is going to be warmed from -35 degrees Celsius to 0 degrees Celsius. Okay, so that basically means we have to cross this line. We have to cross -24.5 degrees Celsius. Okay, so we could start off here and pretend that this is -35. So we're going to do that. We're going to keep going. Okay, we have to cross -24.5, and let's say that right here is 0. Okay, so what did we do? We went from the solid phase, straight to the gas phase. And so what process is that? Sublimation. And finally, we're going to take a look at how wonderful water is. Now, water is a liquid at room temperature, which is very weird because it has a very small molar mass, about 18 grams per mole. And if we compare other molecules that have similar molar masses, such as these two, they are gases at room temperature. And the reason why water is liquid at room temperature, I hope you guys already know this at this point, is because of the hydrogen bonding that's involved in water. If you take a look at just one water molecule, it can form many hydrogen bonds with different molecules. Also, another reason why water is so wonderful is because it can dissolve many ionic and polar substances. Okay, our bodies are generally made of 70% water. So we need water. We have to consume water every day so that vitamins and minerals can be absorbed in different parts of the body and waste can be excreted from the body. Okay, so it's important to stay hydrated. I think the general rule is you could survive about 3 days without water. But that's assuming you are a very healthy, fit person to begin with. We've seen the effect water has on coastal climates when we were studying about thermochemistry. So the climate around the coastlines, they don't vary too much throughout the day. If you compare that with, a day in the desert where there really isn't water in the atmosphere, in the air, you're going to see a drastic temperature change going from morning to night. And that's because water has a very high specific heat, so it can absorb a lot of heat and prevent any drastic temperature changes. Also, don't forget that water does expand when it freezes. That's why ice has a smaller density compared to liquid water. So if you're going to try to freeze some vegetables, you can technically do that, but just realize that water is going to expand. So if there's something that has a high water content, like this head of lettuce, those plant cells are going to burst when you freeze this head of lettuce. So when you take it out of the freezer and thaw it, it's going to come out limp, and this is not very pleasant to eat. So I highly suggest to not put your own vegetables in the freezer. Here's a very nice graph of main group hydrides, and it shows how molar mass and hydrogen bonding affect boiling point. So if you take a look at any of these lines, any of these colored lines, you could see that as we go down the column, the molar mass increases, so the boiling points would also increase. But if we take a look at NH3, HF, and H2O, we see that these three do not follow the trend. And that's because they like to have fun. They form hydrogen bonds. And so that's why their boiling points are higher than the rest of the groups. Now, water, its boiling point is higher still because, again, one water molecule can form many hydrogen bonds with other molecules.